Next to the packet size, there's another thing that people ask, as I said, mentioned before, complexity, and complexity is related then to energy consumption. And here you do two things, right? You're using energy for transporting information, for example, over the wireless link with RF baseband, or you're using energy to do the computing for the actual coding. Now the question, where should we spend the energy? On the coding or on the transmission, right? So for example, if you have uncoded, you don't have to pay for the extra encoding vector, you just send, and if there's a problem, you resend, like an RQ. Or should we do the coding and say, maybe with the coding we have to send less? And this is a trade-off, and we will figure this out here. And we have this done very classically. Instead of, you can have models and simulation for that. The easiest way is you just take the devices, right? As you can see, a little bit older devices. We are currently repeating something like this, but the results will be more or less the same. You have here the Samsung S2, Sony Xperia, and an A version of Samsung. I don't remember what it was. And in order to measure the energy, what we did is we cut out the battery, and it's now served by this Agile machine. Very precise. You can find out how many joules we are really using for a certain service there. Not so easy to take the battery out and just adapt it to it. There are some tricks that the phone will recognize its own battery. And these tricks become more and more complex, because the manufacturers want that you buy their battery. And in newer phones, you don't even have the way to exchange the battery. It's in there. So taking it out, it's more nightmare. You're destroying the phone, which is not really the issue, but getting it out and then taking the battery away and the whole system does not start. This is an issue. So one simple thing is the phone is measuring the inner resistance of the battery. I think it was 82 kilo ohm for the Nokia phones. Others have different values. So they find out if it's really their own. And now there will be chips involved, so you have to find out what is the signature of the battery so that it starts and you can really measure that. But this is only a side note. For the coding, what we did is we said, okay, we take these 4 different field sizes, binary 2 to the 8, 2 to the 16, binary extension fields, and then the optimal prime field 2 to the 32 minus 5. And if you remember that the larger the field, the more complex it became, you will use more energy. But this was also something where the speed up was better, right? If you remember on the PC values that I showed it to you. So this we are using for the coding. And then in the measurement, what we said, okay, let's take the mobile phone. We have some data. We give it to KODO, do some field parameters to it, and then the coded packet will go out over Wi-Fi, and we could send it then to the other side and do the decoding, and then we measure what happens here. So, and this is then the energy consumption. We are giving you the power values, which we are measuring, and then by time it's like this. What you see, there are 4 regions for coding. There are other processes and components that we cut out, and then there's Wi-Fi transmitting and receiving. So if you take for the different phones, right? So this is the computing, and here we are sending, here we are receiving. You see already that sending is more than computing, right? The question is only how much computing you need for how much sending. That's a different thing. And this is a table where you then see the different generation sites going from 2 to 512 packets per generation, different phones for binary, different phones for 2 to the 8, and so on and so on. Encoder on the top, decoder on the bottom. So now there's a lot of numbers. And here you see the resulting plot. Now we say energy in microjoule per bit over the generation size. The solid lines here are the decoders, and the dashed lines up here are the transmission. And this is the plot where we can find out whether you have understood or not understood the whole lecture or the basic concept of coding. Let's just talk about this kind of coding lines. So I think it makes a hell of a sense that the energy consumption goes up, for example, for the binary, when the generation becomes bigger, because your matrices become bigger, you have more to compute, and then you will see, okay, it goes up. But if you see the color code, then you see it's binary. The next one is 2 to the 8. Then the next one is 2 to the 32 minus 5, and then there's 2 to the 16. This is the result exactly from the speed measures that we presented you before. When we said, okay, we are always going down in the speed the higher the field, but optimal prime field was a little bit different. Okay? So and then up here you have two different transmission modes, 1 megabit or 8.8 megabit. So it doesn't matter which we want to take. Forget about the 8.8 megabit per second here. Take the 1 megabit per second plot over here. And try to explain this behavior. Why we have this kind of curve. And what do we see there? I will give you some time to reflect it, but can you explain what we are seeing here? Anybody who wants to try to explain how this curve could have resulted? What is the reason that we have this behavior? So I give you a hint, right? This is the energy for transporting bits. This was the coding of the bits. Now you have, which kinds of bits are we transporting? So we have always the same original data. But we have to code it, and we are transmitting the resulting. So the size of the resulting bits depends a little bit, right? So let's look here. When we go with very small generation size, this color code, what is this curve? Can you see that? This is the binary, okay? So the binary, the others are flat, right? Very flat. But the binary fades out a little bit here, and it's logarithmic, so there's quite some significant more. What is this behavior? Where does it come from? In general, if you hear binary, there should be a reflex where you should spit out something. What was the difference from binary to the others? The 1.6 extra packets, right? So, and when you have a small generation size, down here, this 1.6 extra packets per generation will have a huge impact. Okay? So for example, for 2, we know it's not 1.6, it's a little bit lower than that, but you get an extra penalty. But this penalty vanishes the larger the generation sizes, okay? So we are sending more, here we are sending more bits because we have to repeat due to the linear dependency. Good, let's go to the other side. The same fading out here. But in this time, our binary is not affected. He's staying still, but the other are fading out. What is this? Why do we transmit more bits? This is the message. Why do we transmit more bits when we have higher fields for large generations? Try it.
Because with a higher generation size, we have a problem that, for example, when we have 200 traps generation size, the last few packets can be the same as its old one. So the probability to receive a new one gets down lower.
Not really, because then the black one would have even the same problem. Even the binary here will tell you I have the most duplicate packets. But these duplicate packets do not interfere, because if the definition of overhead last time, we had 2 dimensions of overhead. One is really repetition of the whole packet due to linear dependency. And the other overhead is encoding vector. Here you see the encoding vector. This is G multiplied logarithmic 2 of the field size. So now the encoding vector kicks in. Now, if you look at applications where we normally are, 8 to 37, to 2 is 8 to 32 in the generation size is where we are operating, right? So then this fading here is not even there from the higher fields. Be a little bit careful with smaller generation size for the binary. Yeah? But these are very nice plots, and you have to understand why this happens. Okay. Good, there's another plot where you bring this all together. This is transceiving and encoding, decoding energy ratio for the generation size, not so important. I think the one that was there before was way more interesting. Now, if you don't look at the point-to-point, if you think about point-to-multipoint, then you would say, okay, what happens if I have a transmitter transmitting the information to multiple receivers, right? We investigated this as well, and there the encoding, you pay for the encoder only once, multiple times for the decoding process, and then you also have energy for the receiving and for the transmitting. And this is quite interesting, a plot where you see the energy saving gain over the generation size for different field sizes. And the biggest gains you get, for example, if you have high generation sizes, then you can switch to binary. Before that, there's a phase of 2 to the 8, right, where this is the best. Just to tell you, you can do the same as in the model. There are some papers for that, how you can do this also for point-to-multipoint.